Welcome back. We start module 6, which is residential mobility and location choice models. And in lecture 26, we start with discrete choice theory. So the different concepts that would be covered in this lecture are discrete choice modeling, alternatives, decision rules, utility theory, probabilistic choice theory, and then finally the multinomial logit model. So, discrete choice modeling basically means we have to choose, and it's a discrete choice that we are talking about. And most of the situations we face in our life involve some sort of decision making, which involves choosing something out of a set of alternatives, like choosing a mode of travel, choosing a location to stay, and all these different choices play a role in the urban land use transportation process. So choices can be defined as an outcome of a sequential decision making process. For example, if you see in the particular image that has been given, the figure that has been given, first we need to define the choice problem. For example, how to choose a location. Then the generation of alternatives, that means the location could be near CBD, or it could be in the CBD, or it could be in the suburbs. So this is like the different alternatives. Then comes the evaluation of alternatives, which actually means that out of all this location, based on different criteria like maybe price of house, ownership, regulations, amenities that are present, we decide on a choice. And then finally the choice, that means using this particular evaluation technique, I arrive at a particular choice. Maybe I have chosen to stay in rental apartment near CBD, and finally implementation of that choice, which is actually the moving in process to that particular house. So this is the basic choice making process that we have to, every individual needs to go through. So the process of decision making has got 4 elements. First the decision maker, next the alternatives, next the attribute of alternatives, and then the final decision rule. Now decision maker is supposed to be a rational being. He can be an individual, he can be a household, or it could be a farm, somebody who actually takes a decision. And then alternatives are defined as different options available to the decision maker in a particular context or a particular environment. And it could be also noted that a single decision maker do not consider all the alternatives, because for example, when I am choosing a house, I am not going to look at all the houses in an urban area. I am only going to look at certain houses or a certain set of amongst a subset of all the housing that is available in that particular area. And we can say that we only consider a subset of the universal set of available alternatives, and even further down we can only have a smaller set within that as well. So this is, that means even though there are a lot of options available, the decision maker only evaluates some of those options and then choose something out of them. And then decision maker, the next thing is decision maker evaluates the alternatives available based on their attributes, and that means on the different characteristics of the attributes. And then finally, when multiple alternatives are available, decision maker applies the decision rule. That means he uses some principle or based on which he takes a decision, and he evaluates the alternatives and then makes a choice. So either he can rank those alternatives in terms of what is the first choice, second choice, third choice. He can do it like that, and then he finally makes a choice. So this is the basic process of discrete choice modeling. So by alternative, it is meant that the choice set is determined by the environment, this is basically the universal choice set. It includes all alternatives, and as we were discussing, the subset of this universal choice set is actually feasible for an individual. That means there is housing, but maybe only some of the housing fits in his budget, or maybe only housing in some of the zones which are near to his office, those only is the one he is be looking for. So that may be there is a feasible option or a subset of options that he can look into. This is called feasible choice set for that particular individual. And then subset of the feasible choice set which an individual actually considers, that is called the consideration choice set. That means even though there may be a lot of options which he can afford, like for example it is within his budget, but he still limits his choices only to a few choices which are more close to his particular location. So that could be another level of consideration when he actually decides that out of this particular alternatives I will choose. So this has got a big role to play in the modeling process, because when you are modeling for millions and millions of location in an housing options in a big urban area, it's difficult to model that kind of a choice. So basically this person will actually limit his choice only to a certain alternative or a certain kinds of alternative, and then finally when he actually does the choice, it would be even based on a smaller set of alternatives. Then attributes of alternatives basically refers to the different attractiveness of an alternative is determined by the value of its attributes, and the measure of uncertainty about an attribute is also included as part of the attribute vector. That means it's not only about the things that is known, there are unknown things about that particular attribute which are also considered. And attributes of alternatives may be generic. That means this is they apply to all the alternatives equally, and then there would be alternative specific. That means they only apply to a subset of alternatives. For example, if I say that there is travel time when we are doing a mode choice kind of problem, then every mode there is a travel time involved. But in case of transit, there is also the travel time is not only the travel time inside the mode, but also access to the bus stop. So that means the travel time over here is looked into in a little bit different way. So that means there we will have alternative specific variable which is like access time to transit stop only for the transit alternative. So out of these three alternatives, maybe car, maybe personal, maybe two-wheeler, then transit, we have for transit there is a extra variable in addition to time and cost of travel. This is time to reach the stop. So that's the alternative specific variable. So in addition to all this, we also need to include variables which are related with policies. That means attributes whose values can be changed through proactive policy measures can be included. For example, how a new transport facility will improve residential choices. So that also could be considered while doing this kind of discrete choice modeling. So the next thing that has to be looked into is the decision rule. That means whenever the decision rule that can be applied are dominance. There are several ways we can take a decision. For example, this is based on dominance or satisfaction or lexicographical rules, or based on the utility of that particular choice. Now dominance refers to one attribute, it says that one attribute is better than all other, and this rule could be used to exclude alternatives. That means we can say that that other alternatives are not good, only one attribute is the best and that could be chosen. And then level of satisfaction, that means this decision rule is based on the decision maker and their level of satisfaction with that particular alternative. So decision maker may be satisfied with one of the alternatives, or he can have different satisfaction with different alternatives. Based on that, he can choose the alternative he wishes. Then comes the lexicographical rules, where attributes are ordered as per their importance and decision maker chooses the attribute as per their choice. That means ranks are given to the different alternatives, but then the decision maker decides on any one of those alternatives. And finally comes the utility maximization rule. This is the most popular rule that is being used, and this is based on two fundamental concepts. One is attribute vector characterizing each attribute can be reduced to a scalar utility value for that particular alternative, and that means the different characteristics or variables that define a particular attribute, it could be brought into a scalar quantity. That means it could be brought to a unique value, and individual selects the alternative which has got the highest utility value. That means whichever option has got the highest value, that would be chosen by the individual. So this utility measure is the most widely used decision rule that is used in the choice modeling process. So, in utility theory, it is stated that the choice process can be represented in this way, where choice is equal to a function of characteristics of both decision maker as well as attributes of the alternative. So, we create a utility value which is a scalar quantity, and that depends on the different characteristics of the alternative and also the characteristics of the decision maker. So, both play a role in the final utility of that particular alternative or that particular choice. So, alternative I equal to 1 to L is the choice set, and each alternative is characterized by a utility UIT. So, this is the utility value. So, I is for the alternative and T is for the individual. So, this is which is unique for each decision maker because of variations in the attribute of alternatives and the characteristics of the decision maker. So, decision maker T will choose alternative I if and only if utility of IT is greater than utility of JT. So, this actually means that I is preferred over J. So, that means that this particular option I is preferred over J. It does not mean anything else. Utility of IT is greater than utility of JT. So, we are only looking at the difference between the alternatives. So, the primary implications of I preferred over J basically means there is no absolute reference for utility values. That means the actual values of the utility does not play much role. The difference in utility between pairs of alternatives, that means UIT minus UJT, if that is a positive value, that actually plays a role, and either positive or negative, this part is only important, and any utility function that will result in the same order or ranking will result in the same choices are equivalent. That means if I divide this value by another value by theta, or we multiply this by another value, the result remains same. So, that means any utility function that will result in the same order or ranking will result in the same choice are equivalent. So, that means there is not much difference in those particular. So, absolute measure of utility is not doesn't much have any difference. So, the numerical value of the utility is not important. So, probabilistic choice theory, the problem is whenever we have got this fixed utility values, as per the deterministic utility theory, it is said that all similar individuals with same characteristics will make the same choices given the same set of alternatives. So, that means every time when this individual or a group of individuals having the exact same characteristics and the exact same choices having the choice characteristics are also same, they are given the same set, they based on the utility theory they will only choose one alternative because utility of one would be higher than another. But that is actually not the case. Now, choices we take our day to day life examples, like we in 90% of the time we choose to take our own vehicle maybe to office, but 10 days we may choose to take a taxi. So, the reason being maybe that particular day I was not feeling like driving. So, that means choices vary from day to day for maybe some reasons are there, or there may not be some observable reasons. That means even though I know that because I was not feeling like it, somebody else who is trying to decide that why that particular individual, means myself, has taken a taxi instead of a car, he probably will not know that I was not feeling like driving about it. So, that means the modeler will have no reason to understand this. So, then the next thing is incorrect information or perceptions about attributes of alternatives. So, the next thing is people don't know the exact information about every alternative, and he doesn't understand, he doesn't he has got some perceptions, that means he believed that value to be something, but actually it is different. So, all these things also play a role, and modeler, the person who is actually developing these models, he may not have he may have incomplete information relative to the decision maker, or may not understand the utility construct or the function that the decision maker actually uses to decide. So, the person has actually chosen something, but I being trying to decide the reasons why the person has chosen this, I may not know everything because I am not that a person, and I may not have, and I may also form an incomplete utility equation. So, that means, so these are the issues that plague the modeling process. So, random utility or probabilistic choice model considers this lack of information. That means either lack of information on the part of the user or the part of the modeler, or basically it also takes into consideration that for no observable reasons when people vary their choices. If this is the situation, we say that alternative I is chosen given UIT has the largest utility, and this is the basic form. This could be expressed as a probabilistic way, where this is the equation where P of the probability of choosing I from a set of alternatives C is equal to probability of UIN greater than equal to UJN, and this is subject to J is a part of this Cn. So, Cn is the choice set and J is one of the alternatives and J are the alternatives. So, UIN is greater than the other alternative utilities. So, we take probability of that, and so this is the form of the probabilistic choice model, where we say that the utility of the decision maker T, the utility that decision maker T attributes to alternative I can be written as UIT is equal to VIT plus an error term, which is given like this, where UIT is the true utility of the alternative I to the decision maker T, and VIT is the deterministic or observable portion of the utility. That means this is the part the modeler know or that particular person knows, and this is the part which could be estimated by the modeler or the analyst, and the error term or the portion of the utility unknown to the analyst. So, that means this part the error doesn't, the modeler or the analyst doesn't know. So, we include that component also as a error term in my utility equation. So, UIT is both a deterministic part plus a error term, and the deterministic part could be expressed in this particular way, where we have beta 0 plus beta 1 x1 plus beta 2 x2 and so onwards, where beta 0 are the coefficients and beta 1 and x1 x2 are the different characteristics of that particular alternative that we are considering. And beta 0, as you know, we have discussed earlier that beta 0 takes care of alternatives which are not there in the equation. So, takes care of the characteristics which are not included in the equation. So, we can make different. So, this part is the unknown, this part is unknown. So, different assumptions about the distribution of the random variables associated with the utility of each alternative result in different model forms to predict choice probabilities. That means, based on the distribution of this error term, basically we decide that what kind of model that we are going to adopt. So, the different missing components included in the error term for each alternative is assumed to have a relatively little impact on the value of each alternative. So, this one is will have a small impact on the actual utility of or the value of the total alternative, and then the sum of these errors will be normally distributed as per the central limit theorem. So, we say that because these are small impacts having on the utility, so we can say that this will be normal, these errors will be normally distributed, and then this will, as we know, normal distribution is like this is the mean, and then there is a deviation from that, and then as per the central limit theorem, this errors will be normally distributed, and this assumption leads to the formulation of multinomial probit model or probabilistic choice model. So, this is the functional form of the choice model that we will be adopting. But this multinomial logit probit model MNP, this is very complex, and this is very difficult to analyze, or from this particular model to determine the beta parameters and all is very difficult. So, instead we assume, instead of a normal distribution, we assume Gumbel distribution, which provides computational advantages and approximates nearly to the normal distribution. As you can see, this deep line is the Gumbel distribution. So, it is more or less same as the normal distribution, and the cumulative density function is plotted over here, and you can say this more or less matches. So, but the problem is the equation used for Gumbel distribution is much simpler, and that could be used to develop, and which is easy to solve, and this could be used to develop that multinomial logit model instead of multinomial probit model. So, assuming error components are identically and independently distributed across alternatives and across observations and individuals, we can say that multinomial logit model gives the choice probabilities of each alternative as a function of the systematic portion of the utility of all the alternatives expressed as probability of choosing alternative I equal to 1 to j from a set of j alternatives, where PRI, this is probability of I, is given as e to the power ui divided by summation of e to the power uj, where j is equal to 1 to j. So, that means PRI is the probability of the decision maker choosing alternative I, and uj is the systematic component of the utility of alternative j. So, this is the functional form of the multinomial logit model, and this is possible we are assuming a Gumbel distribution for the error term instead of a normal distribution, which would have led to the multinomial probit model. So, because we are using the MNL model, it has got MNL probabilities has got a sigmoid shape. That means since the output is transformed using a logit function, the probability of each alternative or choice ranges between 0 to 1. That means that is the range. The probability of an alternative could be either 0 and it maximum could be 1. That means it is chosen. So, either it could be somewhere in between. And the shape of that probability, that utility of an alternative, that probability takes like this, where we can see that gradually it takes the shape of a sort of a S curve or a sigmoid curve, we can call it, and utility of an alternative relative to other alternatives is high, then probability is 1. Utility of an alternative relative to other alternative is low, then probability is 0. And that is the range, the maximum ranges. And we see that at extreme values, that is at over here and over here, the curve has a gradual slope, which implies that when the utility of an alternative is very low or very high, a change in utility will not have a substantial change in the choice probability. That means even though utility changes by quite a lot, there would not be change in the probability too much. And at maximum slope along the curve, the utility of an alternative equals sum of the utility of other alternatives. There, a small change in utility of an alternative can induce a substantial change in the probability of being chosen. So, if it is over here, then the change is very abrupt, and then there is chance of being chosen is much higher. So, in the multinomial logit model, it could be developed for mode choice, like we can have a choice between car, bus or metro, or it could be between neighborhood location choice. The choice could be between neighborhood location number 1, 2 to 10, or it could be anything. And we have two forms of the multinomial logit model. One is the binary logit model, where there are only two choices, and then there is of course the multinomial logit model, where we have multiple choices. And using statistical techniques, the relationship between independent variables and the dependent variable can be predicted. When dependent variable is nominal with more than 2 levels. So, MNL model actually talks about the dependent variable where there are multiple choices. There are more than 2 levels. So, this is the functional form of the equation UIT equal to beta 0 plus beta 1 x1 beta 2 x2. This we have already known. So, this is how we calculate the utility of an alternative for individual t, and then we see that when we, for giving you an example, for in a mode choice model like probability of car, probability of bus, probability of metro, we see that probability of car is equal to e to the power utility of car divided by e to the power utility of car plus e to the power utility of bus and e to the power utility of metro. This lower part is called the log sum part. So, that means this is the summation of the probability, e to the power probabilities of all the different modes, and this could be written in this particular form, where j is equal to car, bus, summation of j is equal to car, bus and metro, and e to the power uj, and this is the form which we adopt in a multinomial logit choice model, and the bottom denominator is also known as the log sum. So then we talk about two properties of MNL. One is called the equivalent difference property and the other one is the independence of irrelevant alternatives. So these are two primary properties which have been used in many of the models that are being developed. So we will discuss about that later on. So in the equivalent difference property, the choice probabilities of alternatives depend only on the differences in the systematic utilities of different alternatives and not their actual values. So that means the choice probability of the alternative depends on the difference of the systematic utilities and not their actual values. This we have discussed last time, where we have shown that adding a particular dividing by theta or something will not have any effect, because we are only concerned about the difference between the properties. And considering as for in this particular case, we consider a small incremental change delta u is added to the utility equation of each alternative, like over here. So e to the power ui. So we have added delta u, and then over there at the bottom we have car, we have got bus, we have got metro. So we add delta u to all the alternatives. So we can take this e to the power delta u out like this, and this is common in both both at the top and the bottom, and then definitely it results in the same equation. So this is what we have talked about. So in the same way, if instead of adding delta u we add minus u car, this is what we are adding into this equation, and this will result in e to the power u. When we are determining the probability of car, e to the power u car into e to the power minus u car, that means they will cancel out and they will become 1, and then this becomes e to the power u car minus, again it will cancel out, it becomes 1, and this becomes e to the power u bus minus u car, and then this becomes metro minus car. So the equation has now changed into a different form. So the probability equation could be written in this format: probability of alternative I is equal to 1 by 1 plus summation of j equal to I, where e to the power uj minus ui. So that means for all j's, we have to see the difference between j and another alternative, which is ui, which is under consideration. So if we can develop our equations, utility equations in using this form, that also will help us to develop a multinomial logit model, or we will be able to solve that particular model. So when we do this, we will see that we total uj and minus ui will have betas 0 plus beta 1, beta 2, beta 1 x1, beta 2 x2 for uj, and same for beta 0 plus beta 1 x1 for ui, beta 2 x2 for ui, in that way. So if in this particular sense we can take the variables common, we can see that beta 0 from the first equation and beta 0 from the second equation, they could be taken as a combination and they could be taken as only one variable. So sets of parameters could be replaced by single constraints, and one alternative is set as base or reference alternative. Like in this particular case, I is the base alternative. We are finding the difference between I and the other alternatives, and preference parameters are set at 0 for base, and other parameters are set as preference differences relative to the base alternative. So everything is determined based on that, what is the base alternative. So this is the form. We will show this in details in later chapters, how this is actually used to develop the models. But in this particular option, this particular property actually can convert the MNL model into this particular form. The next property is independence of irrelevant alternatives. This is called the IIA property. This property states that for a decision maker, the ratio of probabilities of choosing two alternatives doesn't depend on the presence of any other alternative. So that is, probability of choosing A over B will not change based on whether a third alternative is present or not. So here in this particular equation, we already know this particular equation. Probability of car is e to the power utility of car divided by e to the power utility of all the other modes. So we also say that probability of car divided by probability of bus as per the IIA property is e to the power, if I equate these two equations, we can say it becomes e to the power u car minus e to the power u bus, which actually could be written as e to the power u car minus u bus. So basically what we are saying is probability of choosing A over B will not change based on the third alternative, which is car and bus will not be affected by metro. So only these two alternatives are important. So this is one property that this property allows the addition or removal of an alternative from the choice set without affecting the structure or parameters of the model. So this property is also used when we develop those models for mode choice or for location choices and so on, and there only one reference category is taken, and we can only, even if we remove one alternative, then also it doesn't matter. The other alternatives are we can always compare the relative proportion of the other alternatives. So not all alternatives remains to be there in the models. So how do we estimate this particular logit models? So we use the maximum likelihood method, and this is used to estimate the parameters by maximizing the likelihood of the observed choices as per the model. So we will do this in detail in a later chapter, but what we can show you is the joint probability density function or the likelihood function is developed based on the observed samples. Like this is the formula for that likelihood function, and their parameter values which maximize the likelihood function is estimated by finding the first derivative of the likelihood function and equating it to 0. So we take the first derivative of this particular function and we set it at 0, and for which values of this beta parameter this value becomes 0, those values would be adopted as the coefficients for this particular utility equation. So basically this is a product of this probability of j and t. So this, for each of the beta values for each of the characteristics are considered, and then delta jt is equal to 1 if chosen indicator is equal to 1 if j is chosen by individual t and 0 otherwise, and pjt is the probability that the individual t chooses alternative j. So basically we write that particular whenever we form we have the actual data for people choosing different alternatives. When the alternative is chosen, then we take delta this jt is equal to 1. If it is not chosen, it is taken at 0, and we use the utility equations over here, and then we take a product of them, and then this forms a likelihood function, and we maximize these values and then take a derivative of that, and we try to equate it to 0 to find the values of those beta parameters. This would be explained in detail in later chapters, but to determine the beta parameters, we use softwares, and the softwares actually uses this maximum likelihood method to determine the coefficient values for each of those parameters that forms the alternative characteristics for that particular alternative. So these are the two references that you can use, and in conclusion we can say that discrete choice models are used to analyze and predict the decision maker's choice of one alternative from a set of finite and mutually exclusive alternatives. These models are able to predict decision of a group of individuals, like in an aggregate approach, or an individual in a disaggregate approach using probabilistic approach. Multinomial or binary logistic regression can be used to estimate relationship between dependent variable, which is choice, and independent variables which can be continuous, like interval, ratio, or categorical, or it could be categorical variables like ordinal or nominal. So additionally, this helps to determine the relative influence of different attributes, alternatives and decision maker characteristics on the choice outcome. So that means we can formulate models for both binomial and binary and multinomial logistic regression models, and we can formulate the effect of each of those characteristics, and the relative importance of those characteristics could be also determined. Thank you.